Okay, coupled first order simultaneous equations. So these are often used to model predator-prey models. So you may well see that. We're keeping it relatively simple, so we're only looking for equations of these two forms. So dx dt equals ax plus by plus a function of t, and dy dt is cx plus dy plus a function of t as well. And we basically solve by eliminating a variable on differentiation, but I think it's best just to show you an example. So this is example 12 on page 186, but I've just kind of cut the wording down dramatically. So we've basically got, after t years, the number of bears is x, the number of fish is y, and they're modelled by these two linked or coupled first order simultaneous equations. So they're first order because we've just differentiated once. So we've got dx dt and dy dt. These are homogeneous coupled first order simultaneous equations because f of t and g of t here are both equal to 0, so they're known as homogeneous ones. And the first thing is to show that this here is true. And so what we're going to do is rearrange the first equation. So we've got to rearrange one. And that gives you that y is equal to 10 dx dt. So I've multiplied 2 by 10, subtracted 3x. I'm going to come back to this equation later, so I'm going to just pop a 3 next to that just so I can refer to it later on. And then we can differentiate y with respect to t. So differentiating y with respect to t. So I'm basically differentiating both sides of the equation with respect to t. So this goes to 10. Let's solve the second derivative. So d2x dt squared. And then if you differentiate x with respect to t, you get 1 times dx dt. So that gives you that there. So you're basically doing implicit differentiation through there if you think about it. And then I can substitute both of these into 2. So you're rearranging one, differentiating, substitute into the other, and that's your method for this. And so substituting in here, 10 lots of d2x dt squared minus 3 dx dt minus 0.1x, and then multiplying this through by a half, so plus 5 dx dt minus 1.5x takes you to there. And then tidying that up, I've just realised I haven't got an equals sign. Sorry, equals minus. Okay, looks a bit happier. And then if you rearrange that, you will get the thing that you're showing. You could just sort of check that you're happy they're the same, but don't forget to write down the thing that you're showing underneath. So that you kind of work through that. So that's your method there. And then section B, we're going to find the general solution for the number of bears. So that's nice and easy because you're just solving this homogeneous second order differential equation. So we can just look at the auxiliary equation, which is m squared. Take 0.8m plus 0.16 is 0. Pop that into your calculator. You get a repeated root at 0.4. And so from there, it's just general form. So x is equal to, sorry, got a problem with equal to signs. X is equal to a plus bt e to the 0.4t. So we've done a lot of that, so you should be quite happy with that. To find the general solution for the number of fish, you could repeat the whole process. So you could rearrange the second one and substitute into the first. But instead, we've got this equation here, and we also have that one called 3, which is y is equal to 10 dx dt minus 3x. So what you can do now, you can actually substitute from here into here, but we just also need dx dt. So once you've got x, you can differentiate. So dx dt. So I'm doing product rule, so it's v du dx. So this is going to be e to the 0.4t plus u to v dx, so it would be 0.4 a plus bt e to the 0.4t. And so substituting it into here, y is equal to 10 lots of dx dt, so 10b e to the 0.4t plus 4a plus bt e to the 0.4t minus 3x, which is a plus bt e to the 0.4t. So go with that method for those. It's a general rule. And then tidying that up, we end up with y is equal to, so we've got 4a minus 3a, which is a e to the 0.4t, and then 10b e to the 0.4t, and then plus 4 minus 3 is 1, lots of bt e to the 0.4t, so it takes you to there. When t is 0, there were 5 bears and 20 fish. And so we're looking at here and here, and we really need to find these constants a and b. So when t equals 0, there were 5 bears, so x equals 5. So substituting into there, t equals 0 gives you 5 equals a. And then t equals 0, y equals 20. Substituting into here, they look worse than they are. So 20 is equal to 5 plus, that one's going to go to 0, so plus 10b. And so b is equal to 1.5. And we want the number of bears, and so that's x equals 5 plus 1.5t e to the 0.4t. So just trying to keep it on one board now. When t equals 10, x is equal to, so if t is 10, we've got 5 plus 15, 20 e to the power 4, which comes out as 1092. And then part E of this question, let's squeeze it on there, was actually criticise the model. And if you're looking at what's happening here, there's growth without limit, which is unrealistic. That's quite a common thing to criticise on a model. So the model predicts, so it's not the most sophisticated of models for predator-prey. So model predicts number of bears will grow without limit, or indefinitely, or words to that effect, continue growing forever, which is unrealistic. So this question is kind of the nuts and bolts of what you need to do with these linked, keep them linked, coupled, first order simultaneous equations.